The broadcast is now starting. All attendees are in listen-only mode.
Good morning and welcome to the Harvey Rock Physics course on LogScope and the petrophysical evaluation that can be done with it. At the moment, you should be able to see on your screen the LogScope Petrophysical course dated April the 11th, 2019, which is today. The items that we'll go through are listed here in order. We're going to go through LogScope and we're going to spend about 5 minutes showing how one can download it and register the software and also apply the activation code. Then we'll show you how to load LAS and delist data, present a basic simple plot, and show you some of the editing and curve manipulation functionality, and then a cross plot. Okay, the basic functionality of LogScope, because the basic functionality in LogScope is to select a track. You simply do that by tapping on the track and it will highlight yellow. To select a curve, you just tap on the curve title. To select shading, you simply tap on the shading and you can select the shading. Selecting an annotation, tap the annotation and then select the annotation on the plot, and we'll show that kind of functionality. We've then got edit. You tap to edit a selected object, and then an edit button will contextually appear and you can edit that. To delete, tap to delete selected object, and then changing scale is done by using a 2-finger pinch and squeeze, or by using the preset scales that are at the top of LogScope. The curves and shading can be selected by using text searching. So these are some of the gesture functionality to keep in mind as we walk through LogScope. The example data set that we will use is available at this web link. So the whole webinar is going to be recorded, so you can actually go back through the webinar and reproduce some of the things that we've done with the data in that in that data set. Okay, before we start on the what the logs measure, we'll go through LogScope first. So on my screen, I have a Windows Surface tablet, screen mirrored, and an iPhone, and we'll be duplicating what we do on the iPhone as to what we do on the Windows tablet. So if I move my mouse over, LogScope is started by tapping on this option, or double clicking on it in the usual fashion, and you'll get LogScope showing up with the wells listed on the left. Obviously, if you're starting LogScope from scratch, you'll have nothing there. Then we have our demo well, and then we have import, which allows you to import a variety of different formats. You can import LAS, DLIS, and the LogScope archives, and there are a few others as well that it will accept there. At the top of the screen, we've got two icons, a portrait and a gear wheel. The portrait icon allows you to define your or register your user account, and then you can purchase, you can see what subscriptions are active. LogScope for the Windows allows you to have two devices active at any one time. You can change your password, you can edit your details, and obviously you can log out or log in. You only have to do this once, and an internet connection is required to do that connection. With the preferences, in preferences you can actually define your plotting template. You can define whether the demo is shown or not shown. You can define the default units. You can define the scale, and you can define the position that the wells will be open, top or bottom. Some people, on some versions of Windows 10, we have included an option called single row menu to allow people to use those particular versions of Windows 10. We'll get to the iPad in a minute. We're going to move on to the iPad in a minute. But down the bottom here, you can choose your grid and your grid color, annotation color, and the cross-plot point size. I generally select the point above the smallest point size because I find that's the best, but it's a matter of taste. In the map view, you can actually use the well name rather than this well name here. And this well name is the actual API well name that appears in the well header, and we'll talk about that later.
Is the iPhone display muted by any chance?
Yeah, the iPhone display is turned off. I'm now going to move to the iPhone display, which is the same as the iPad. So we'll just fire that up by using the iPhone, by using the LogScope symbol on the iPhone. And again, we have the same thing here. So we have edit functionality, which allows you to select multiple wells. We have a map feature to show maps, which we'll get to in a minute. And then we've got the account, which brings up the account menu. And this is exactly the same on the iPad. So we have the username, the purchase subscriptions, and so on down to log out. On the iPad and the iPhone, to enter the activation code that we supplied you, you swipe to the left, and that allows you to see the activation code, and you can enter the activation code. Okay, so the settings, again, we've got preferences, and in the preferences, they're pretty much exactly the same as on the as on Windows and on the iPad. The iPhone will have slightly different character in presenting things, in that it has to accommodate the information on the screen. Another functionality with the iPhone and the iPad is if you rotate, I'll just move that to the front. If you rotate 90 degrees, you will see everything in landscape. And when you go to use AirPrint printing and so on, it will actually print out landscape rather than portrait. So on both of these, we've got exactly the same wells. I'm going to go back to the portrait mode, and I'm just going to put the iPad and the iPhone to the side for a minute, and show you how to load a well from the last file. We'll do the example well, and then we'll run through some of the basic functionality. So if we press on example, I'm going to overwrite and create a new one, and it loads, and it produces a plot with the curve there. So let me just go back in. And let me just load that again. So this is loaded at the bottom, and you can see the curved tracks here displayed, and I am using my finger to walk down the plot, but I can also scroll using a mouse. Okay, so the basic plot template is a 3-track template, and if I want to select a track, I can tap on the track, and that allows me to add a curve to the track. So I'll add another camera ray, and LogScope will automatically choose a new color for each curve that you add to a track, or it will change, or it will use the default scale as well. If I want to move that curve to another track, I can just tap on the curve and drag it across, like so. This also shows the functionality that you can actually put linear curves on logarithmic tracks and logarithmic curves on linear tracks. You are not bound by a track style being linear or logarithmic. If I hold my finger down or I press the mouse button down on a track, I can move that track by simply dragging it, or I can copy it and then I can paste the track in, the entire track with all the variabilities and all the curve information that's that's available there. So let's just walk through the options at the top. We can add a track, so I'll use my mouse to do that. So if I say add, I have the choice of adding a linear, logarithmic, or a tadpole track. So if I add a linear, it will add a linear track at the end. If I highlight a track and add a track, it will add the track before that particular track. If I wish to delete the track, I can highlight it and delete a track. I can move this curve over to the new track, so it's all by itself. If I want to add shading, I don't need to have any track specified. I can just add the shading like so. And if I want to choose sand, I can just type in sand. And let's just take the fine shading, and I can just drag that and drop it in the track and in the position that I want it. If I want to edit that shading, I have two choices. I can edit using the edit button here, shading, or I can tap on the track on the shading itself, and I can edit the shading there. And in that case, it will highlight the whole plot, which is designed to tell you that this shading, that a shading is about to be edited or deleted. And if I edit, I can change the shading to be between any curve and any set of curves, between a curve and a track, so I can change it to 50%. But I also have the ability to make the shading a log attribute, or we can also use red, green, and blue, which means that you can use 3 curves to color the shading, and each curve is either red, green, or blue. It's extremely useful if you've got a spectral gamma ray, and you can shade them. You can shade thorium, uranium, potassium, red, green, and blue, and see clay differences more or less immediately. So we'll leave this as a lithology in 50. We can put the shading in the left, the right, or as the shading on its own. I'm going to do the left curve, and like so. And if we just scroll down, you can see the shading is added in here. So some other functionality that we talked about is text. So if I tap on the text button, I can type in a text box, and it puts it on the plot. I can edit the annotation or change its size, and I can change its color, and I can move it about simply by moving it about with my finger. So I've been doing that with my mouse, but with my finger I can do the same thing. And I can also delete the shading here, like so. The next functionality that I want to show is to replicate what I've shown there on the on the iPhone/iPad. So we'll do the same thing here. So I'll move the iPad to the center. I'll change to landscape. And we'll just blow this up so that you can see it. And here I can tap on a track and I can highlight it. And then I can add a curve. We can also add arrays, which can be images, VDLs, and so on. If I want to copy this track, I can just go copy, and then I can paste it in. And now I've got 4 tracks. So to move from one track to another, I can drag curves like so. Okay. To pinch and squeeze, you can pinch and squeeze, and you can display the plot, and you can scroll pretty much as you can on the on the Windows tablet. If I want to move a curve, I can drag it, and it will appear on the track, and I can move it backwards, like so. Now, when you set up a plot, you can save it as a plot template, and the template is here. So if I save this, I can save it as either a global template or a local template. So I'll save it as a local, and I'll just call it basic course. I can do the same thing on the Windows tablet. And I can save the plot template, like so. Now, the next functionality that I'll show you on the Windows tablet is the functionality related to what the software can actually do. So we'll start with the log analysis button. It's a full-featured deterministic log analysis, and we can go all the way down and produce pay flags, rot mechanics, shale gas such as TOC, gas composition, kerogen. We've got coal bed methane, we've got sigma functionality, And we can also produce porosity and V-clay from NMR and the binning from that. Each of these are defaulted to be switched on, but they can be switched off, like so. And if we switch off something like this, or this one, it will highlight red when it needs additional curves. So if you have curves that you need, that you've computed yourself, it will add them to the list of curves that you need to enter. If we leave all the processes on, it's going to compute everything that it needs in the log analysis, and it will populate the curves as it finds them. We have an extensive aliasing table in there, so it's able to identify the curves as we go. For the parameters, you have the ability to zone, and we'll talk about that later. So if I talk about the functions that we've got in there, we've got the functions listed here, and we've got linear and logarithmic, which are basic linear and logarithmic functions. Unit conversions, it allows you to convert the units. Basic gas wetness ratio. We have rescale functionality, which I'll show you, which essentially allows you to rescale data that has, for example, been badly digitized. We've got a number of utilities that allow us to work with casing integrity, cement bond logs. We've got functionality to set values to missing, interpolation, smoothing, solver, scripting, and NMR. So if we go to the Go To button, it allows you to go to a depth or a zone. You can choose a zone, or you can choose a specific depth to go to. And a zone is our nomenclature for formation tops. If I show the same thing on the iPad, the menu down the bottom here scrolls left and right on the iPhone, or if we show it in landscape mode, we can actually see the whole menu. And if you touch the log analysis, we have exactly the same functionality here. It also identifies the logs, and it also has all the parameters in there. The functions, again, we have linear, logarithmic, unit conversion, gas wetness ratio, interpolation, smoothing, and down the bottom here we have solver, which is a basic way of computing curves from a simple equation. It will, because it's a solver, you can solve left or right. You can solve for row matrix if you have all the other parameters as curves, and it will output that as a curve, or so on and so forth. And you can actually save these as equations. We have scripting as well, where we can actually put in a Python scripting, and this is fully functional on both Windows, iPhone, and iPad. So the next part of the display part of this that I want to show is the cross-section capability and the functionality therein. So on the windows, down the bottom of the screen, you have this thing called filter. And here I have a filter that I've set up, and it's got a variety of different, it's got a map box, which is a geographic area from a map. It's got the name, and I've got two names in there, and I'm going to add a third one, core. And these filters can be saved to hold data, to hold a variety of data. So if I go and I select the map view, I have the map of a field in Australia, a well down here, and a well over here in New Zealand. We use the, on Windows, we use the Microsoft Bing Maps, and on Apple, on the iPad and the iPhone, we use the Apple Maps as the basis for that. We have the ability to add shape files and TIFF files as well. So I'll just walk you through the functionality that we've got here. So you can define filters at this level. You can return to the list view. You can refresh. You can select all the wells, select none. You can change the style of the map to be a satellite view or terrain view or road view. And we can zoom to all, or we can zoom to selected. To select a bunch of wells, you can just draw a circle around and select the wells like so. And if we zoom to the selected, it zooms to the selected wells like so. If we want to produce a cross-section, we can project a line through that, and we can pick a line like so, and it will project the wells into the line. And to produce a cross-section, once you've got a bunch of wells selected, you can see you have a whole bunch of additional options. But we're just going to go for the cross-section option. And you can display wells in measured depth or TVD. You can choose the reference datum. You can choose the section that will be displayed. I'm going to cheat because I've already built a template that has all this built in, and I've selected my own template for that. And here we have the cross-section displayed with the formation tops. And I'm using my finger to move this. I can pinch and squeeze and display the wells like so. At the top of the screen, you'll see that there's configure plot, scale, zone, and LAM, which is our log analysis multi-well log analysis option. But I'm just going to talk about the zone here, and if I go edit, I can add formation tops in. So if I call this A, and we've built the smarts into the software once it's defined to be able to drag it up and down. So I can put there, and you'll see when I come to the second well, it calls this A, third well A. It guesses based on the vertical as well as the horizontal distance what it thinks the formation top might be. As I want to use this data set later to show some other functionality in LogScope, I will come back to that. So I will leave that cross section, and I will now repeat the same thing on the iPhone. So here you can see I've got the wells on the iPhone, and if I circle them, you have to excuse my fat fingers, and I can zoom to the selected wells like so. I can add a projected line like so, and I can go to the cross section. I'll just change it to this way. And I can build exactly the same cross section here. So we'll just move this to the front. The iPhone and the iPad have phenomenally fast processors in, and you can sort of see the speed. If you change the scale and you go scale to fit, it does the best job it can. Obviously this has got a small amount of real estate. I can edit the formation tops like I did before. I call this A, and you can see that it does the same thing. I'll discard those. You will see that there's this button under zones for import, and you can actually import multiple wells with multiple formation tops into the software all at once. If I want to go into a particular well here, for example Bliner 2, I can just double tap on that and it will load me into that well, and the formation top and the template that I was last. So that's kind of the sort of basic functionality. We'll just pause now, and we'll answer some of the questions that have been sort of accumulating.
Can you see the question?
Yeah. Okay. The ability to store in the cloud, yes. We are working on some push-pull functionality with various providers of cloud storage, but we use Box as our own storage, and we can import and export data to the cloud storage. Geochemical analysis, yes, is coming. We will get to the TOC computation a little later once we've been through the logs. And log digitization is possible but you have to load an image of the log, and you have to digitize it. We recommend doing this for short sections, not for large sections. I'm happy somebody's mentioned Android devices. We're considering it, but we will be releasing the iPhone version very shortly, and we want to see how that goes. But the iPhone version has pretty much exactly the same functionality as the Windows version. Okay, so we'll go back. I'm now going to go through some more mundane stuff about curves and so on before we talk about computing, V-clay, porosity, RT, and just one of those questions said the TSE computation. Okay, so I'm just what do logs measure? Logs were principally designed to measure fluid types. That is, to measure the presence of water versus oil. And it was principally done initially with the resistivity tool, but as the technology advanced, the ability to measure porosity, and then understanding that lithology affects where you'll find hydrocarbon also became important. So you can say that logs measure all three of those things, and there are different logs that measure different things. The basic types of lithology that we have at the moment is clastic, which defines rocks that have predominantly quartz or can have feldspar grains, and are defined in sandstone, siltstone, or shale. Shale is generally clay with fragments of silt or larger sized particles. So I generally tend to refer to particles less than 1/16 or 1/256 of a millimeter as being clay-sized particles. The porosity, clastic porosity, is generally related to the packing, and the maximum packing achievable in sandstones is 48%. In carbonates, which is the second form of lithology that we deal with, principally in the oil and gas industry, are precipitates. Calcite is formed in a biogenic nature, either coral reefs or as deep sea oozes like radiolarite oozes, and so on. You can see the two classes of reflected in chalk and in reefal deposits, such as the carbonate deposits of the Delaware Basin. Dolomite forms by the addition of magnesium into carbonates, and it has the curious effect of increasing the porosity in general. Aragonite usually forms in the vadose or the phreatic, which is the zone in the reservoir sequence that is exposed partly to air and also deeper into what's called the phreatic zone, which is where the water table starts, and the water is actually in contact with air. In carbonate porosity, you generally produce them as separate bugs, pores, and these bugs and pores are created by the dissolution of fossil fragments or or, or shell fragments within the rock, and they create pore space. In carbonates, you can also create fractures, and this is created by tectonic effects or by the dissolution along the fractures to actually create cavernous type porosity. Both porosities can coexist together in the same formation, but in general, it's the biogenic features that get dissolved that actually creates the porosity in the carbonates. In terms of fluid types, we have gas, we have hydrocarbon, and we have water. And down the bottom, I've put a little table that describes the tool and the sort of things that they can measure. So at the top, the SP is the spontaneous potential, and that measures lithology and fluid type. The gamma ray measures principally lithology. The sonic can be used for porosity. In fact, it was originally designed for porosity and lithology. You see very nice compaction trends in shales and clays from the sonic. Resistivity measures porosity, but is more focused on measuring the fluid type. The reason I say porosity is that resistivity will increase as porosity decreases. So when you're in very tight rocks, you are going to have very high resistivity, very low conductivity, because it requires some kind of conductive media to move. I'm not discounting metallic minerals like pyrite and so on, but principally that's the fundamental media for conducting electrical current. The neutron measures porosity. Again, it was designed to measure porosity, and through observation, it will react in a particular way in different lithologies. For example, in clay, it will show high porosity. The density measures both porosity and lithology, and the PEF lithology. NMR is able to distinguish between porosity, lithology, and fluid type, and dip meters and images, which is a conductivity, measures porosity and fluid type. Practically, they are measuring differences in the conductivity flow in the near wellbore environment. So the log responses that we described there fall principally into three categories: radioactive, sonic, and electrical. And each is designed to provide a piece of the information that allows us to identify lithology, porosity, and fluid type. Using the logs together, it allows you to build up a picture of what's happening in the subsurface. So if we take the gamma ray, the standard gamma ray applications are as the primary depth reference. Little known, in the early days of logging, the spontaneous potential was used for this, and prior to that being used, the resistivity was used as the primary depth reference. It's used for correlating wells to well. It's used for lithology identification, and in high gamma rocks it can be used for inferring organic material, permeable beds, and source rocks. It can also be used for fracture identification, and it can calculate clay volumes and mineral analysis. More detailed information on this is provided in the handout. That's one of the 2 download files in this webinar. The spontaneous potential is a tool that's not used conventionally much, but it is an extremely useful tool because it does allow you to identify the salinity within particular formations. It can also be used for indicating as an indicator of shaliness or clay quantity. It can be used for detecting bed boundaries. It can also tell you whether or not you've got permeable beds. And as I indicated, prior to, I guess, the 90s, it was one of the principal depth reference logs on logging runs. The sonic tool is a wonderful tool in its construction and the way that it actually works. In order to make the sonic tool work between the transmitter and the receiver, they basically create a tortuous path for the sound wave, because in the steel that the tool is built from, the sound will move at 56 microseconds per foot, which means that it will arrive at the receiver before the compressional wave will arrive at the tool through the formation. We use the sonic for calculating porosity, and because it's related to the elasticity of the rock, we can also use it for mechanical rock properties and a variety of other applications, as listed on the slide. Calibration of the sonic tool is not necessary, because in casing it should read 57 or 56 microseconds per foot. In washed out hole it will read 189 microseconds per foot, or the equivalent. So keep those numbers in mind, because you can use them to identify whether or not the sonic has been accurately recorded. And in today, when they're using digital sonic tools with multiple receivers and using semblance processing, it is possible for the semblance processing that you receive from the field to not be accurate. And this is one way of validating the accuracy of the information that you get. Resistivity tools fall into 2 categories. You have the induction application, and practically this tool measures conductivity, which we invert to get resistivity. If we use Archie's equation, we can actually calculate the percentage saturation within the rock. And Archie's equation typically used with a saturation exponent of 2 and a cementation exponent of 2, and A is generally set to 1. So if we look at the Laterlog, this tool measures the actual resistivity of the formation and is a focus tool, and it also measures the same things. So if we talk about the Neutron tool, the Neutron basically measures the neutron count that comes back to the tool from the formation, and that neutron count, when it was just a single detector, was used through an exponential graph to actually calculate the porosity. The porosity was plotted exponentially, and the counts were plotted along the x-axis. Now they use at least 2 receivers, and they take the ratio of the 2 to get the porosity of the rock. The things that can affect the porosity determined by the Neutron tool is clay, and if you have a lot of gas, you will experience, particularly in high porosity, an excavation effect, which means that it's going to give you a higher porosity, or rather there are going to be lower numbers of neutrons reflected back to the tool, and so on. So basically it uses scattering, and the neutrons essentially return to the tool, or the gamuts from the neutrons are measured. Typically, the neutron is presented on a scale of 45 to minus 15, and that's for a neutron that is scaled in limestone units. Limestone units were the original units that the neutron was calibrated in, because they used a limestone block, and they measured the porosity in that and calibrated that to 0 degrees. So neutron measured in sandstone units is a somewhat slightly nonlinear way of computing porosity. It is useful for comparing with the density and other porosity measurements, but typically in areas such as this, and this is in limestone units, you will see a separation, but if you change this to sandstone units, the separation would diminish, and the neutron porosity and the density curves should overlay, giving you the same, allowing you to quickly estimate the porosity from the density. If we talk about the density tool, this is a qualitative measurement. It is not quantitative. It is quantitative, and it is designed to actually measure the density in the rock. When it's combined with the Neutron tool, it creates a very powerful lithology indicator. So whereas you may use one tool, like the gamma ray, in this case using the two tools together will allow you to get a better handle on the lithology within the rock. The density tool can distinguish between oil and gas in the pore space by virtue of their different densities. You will see a change in the density, but it is microscopic. Modern density tools also have a measurement called the photoelectric effect, which can help distinguish between rock lithologies and recognize when heavy minerals and fracture identification. However, if you use barite mud, this tool is affected to the point that it becomes useless. The density is okay, but the photoelectric effect will become useless. In addition to the density can be used to determine V clay, and is probably even more accurate than the gamma ray for estimating clay volume. The density tool is usually run egg-centered and is basically pushed against the borehole wall. So it has a caliper on it, and it also has a long and a short space detector, and the difference between the two of those is called the density, the difference, or delta rho, the difference between the long space and the short space detector. The greater that difference, the more uncertainty there is in your measurement, but that does not mean that your measurement of the density is going to be inaccurate. It's just a quality indicator that can be used for indicating your confidence in the measurement. Typically, the density is calibrated using a standard aluminium block and sulfur block. And a side note is the University of Houston used to have the API pits that we used to calibrate all these, including the gamma ray, and those pits no longer exist. So we're reliant on aluminium, and we're reliant on calibration that have been generated from these pits and are now used into the future for these tools. So it's something to keep in mind. Okay, here's the density theory of measurement. It actually measures the electron density, and using certain coefficients you can actually calculate the actual density of the rock. The atomic weight and the atomic number is used to calculate the photoelectric effect. So presentation for sandstone scales, the density is usually plotted from 1.9 to 2.9. For limestone scales, it's plotted from 1.95 to 2.95. And the amount of density correction is presented from minus 0.25 to plus 0.25. And the red curve on this one is the density curve, and the black dotted curve down here is the D rho curve. When you compare the neutron and the density together here, it's showing up with a greater separation, neutron and the density. This also corresponds to high gamma ray, but these two curves here are telling me, because of the way they cross over, that this is clay or shale, as is down here. Down here, you've got a little sand in here, and you've got clay down here, and these are the sand. And it's incredibly useful to shade these curves. Nominally, people use green for shading when the density is greater than the neutron, and yellow when the neutron is greater than the density, or less than the density, I should say. For lithology estimation, you have these curves that can be used: the gamma ray, the spontaneous potential, the density, the neutron, and the sonic. So the gamma ray reacts to the amount of radioactive minerals in the rock, which usually evolved from uranium-235, 238, and thorium-232. And that's what gives the high gamma ray value in clays, because they generally are made up of minerals that contain high proportions of the thorium and uranium. It's interesting to note that if you use the gamma ray on its own and you're in an area that has heavy mineral sands, it is possible to have sands that have gamma ray values that are equal to or greater than your clay values. And the gamma ray is often taken as the primary indicator of shell content by using the gamma ray log, take gamma ray clean, gamma ray shell, take gamma ray clean. It's just a ratio. But this is a qualitative tool, whereas the density and the neutron can be used as a quantitative tool. And in the next section, once we finish this, we will go through that. So this slide basically shows you some more detailed information on using the gamma ray and clay computation. Now, the spontaneous potential is a tool that I like a lot because it can be used to give you an estimate of the salinity within the formation, but it can also help you understand which formations are clay rich and which are clean. You obviously need to know the salinity of your mud in the wellbore to actually calculate this, but it can be used for calculating a clay content. And here we have the neutron lithology determination. And in this case, we're showing here that we've got compatible limestone scales, and in the limestone, the compatible limestone scale shows the density and the neutron overlaying each other. When we get into the sand, you get the gas excavation effect, and in liquid, you will see a smaller difference between the two because we're on a compatible limestone scale. That means the neutron porosity is in limestone. I think back in the 50s and the 60s, when these scales were developed, the compatible limestone scale is just a beautiful way of looking at your data, because it allows you to estimate the porosity immediately from the plot without doing any sort of computation. You can also estimate the lithology from this information by seeing what the values are. The density lithology determination, we've been through this information, but if we combine the neutron and the density together, you will see on the left we have the neutron density cross plot, and we'll talk about this in a while. And this is the primary tool that we use for estimating clay content. The reason being is that the neutron density is not affected by radioactivity of the rock. On the right-hand side, we've got the PEF versus, we've got the density versus the PEF. And these two are standard cross plots that can be found in any chart book. Both of these allow an estimate of the lithology to be determined and the amount of clay to be determined. The porosity is determined from a number of tools, and these are resistivity, sonic, neutron, and density log. Archie in the 1920s and the 30s, before he wrote his paper in 1945-46, observed that 100% water-saturated clean sandstones and carbonates produced an empirical relationship, which we know as Archie's today. Basically what it says is that the resistivity that you see in the rock is proportional to the volume of fluid in the rock and the type of fluid in the rock. If you have oil in the rock, the resistivity will be extremely low. Therefore, the proportion of conductive fluid in the rock must be very low, and the proportion of hydrocarbon in the rock should be quite high. If we take the sonic tool and we use the Wiley time average equation, we basically take the sonic log value minus the value in matrix divided by the fluid minus the matrix value. There is also a compaction factor that's included, and this is because rocks compact over time. The Raymer-Hunt-Gardner equation takes into account the compaction factor, but in all cases, vigilance is required to make sure that you have the matrix value and the fluid value set correctly before you calculate the sonic porosity. When computing the sonic value, we generally can use a cross-plot methodology as well, and this can aid in identifying the clay compaction factor, and again this will allow us to remove the clay effects from the rock and produce a more accurate porosity. This isn't a very good example, but the orange curve here shows a subtle decrease in the sonic, which is an indication of the compaction. And there are different trends within the clay, within the different clays, that show changes at lithology boundaries that allow you to maybe estimate the amount of erosion that's occurred in an interval based on the sonic compaction. So we've been through the neutron porosity as well, and the the way that LogScope uses these logs is in concert with each other and together. And we'll now head into the petrophysical component of the presentation. Okay, just before we start, we'll just have a quick look and go through some of the questions that we've got. Some of these questions we'll talk about as we work through the analysis.
It's called density. Yes. One more, yeah.
The density can be measured in case hole, but you need to have the right correction for the density, and there are charts that allow you to correct case hole density. It can also be measured in air as well, if you're using an air fluid. So we're not specifically going to address this, but we will send some information on what can be done with case hole density. We got a question about geomechanical logs, and we'll talk about that as we work through a single well log analysis. As much as possible, I'm going to try and replicate on the iPhone what we do in Windows, but we'll just go back to Windows, and we'll start with the log analysis. So I'm going to unselect these wells, and then I'll zoom out to all the wells, and I'm going to add in the example well. And this example well is called Scarborough 5. By right-clicking on the well or holding your finger down on the well, you can open it up. So this is the well, and it opens up exactly where I was last in the well, and it'll allow me to resume. Buttons that we didn't talk about were the trim button, merge, zones, and refresh. Trim allows us to trim the data set, so if you wanted to just look at a limited interval, you could trim and throw away the interval above and below. The merge button allows you to merge in merge in other LAS and DLIS files elsewhere, and also put together data sets. So let's look at the zone functionality first. So I'm going to set the scale as 1 to 5,000. Okay, so we'll just go 1 to 2,000, so it looks a little better. And we show the zones, and then we hit edit. So I know this is the top of my reservoir, so I'm going to click on there, and I call it reservoir. And I can move this up or down. Okay, so I'm going to keep that there and save and exit. Now the first thing that I need to do with the log analysis is to initialize the log analysis. And as you can see, I've got two zones in here now, the reservoir zone and zone 1. So if I tap on here, I can edit these zones together. And the reason I'm doing that is I'm making sure that it's Schlumberger, because I know this data is Schlumberger, and I want to change a couple of other parameters. But instead of searching through the list, I can just type in equation, and the SW equation I'm going to change to Indonesia. Now, I can change the equation to one of any number of equations. I have access to the full Waxman-Smith and UHAS equation, which uses CC, cation exchange capacity, and the UHAS equation for doing the computation. So I'm going to unselect these, because that's the only thing I wanted to set, and you just hit the process button, because it knows that all the curves are there, and we just do the process. Now, firstly, I'm going to come back to these options down the bottom here, which are options that are important. The header brings in all the information from the header, such as you see in the header of a field print. And then we go to run, and we have a list here of all the parameters in there. And these parameters are important for doing an analysis. For example, the RMF value is really important for calculating the true resistivity and for using the SP. The maximum recorded temperature is also important. And if you have multiple runs, you can use those, and those will impact the temperature gradient that's calculated. So if we go to the data view, we have here the default data that we've loaded, but we also have the log analysis group here. And LogScope allows you to mix and match both discrete and continuously sampled groups. The import button here allows you to import core data such as from a CSV file. So I have a CSV file here, and I can import all these, and I'll call this RCA, Routine Core Analysis, and I'm going to change this to text. I'm going to change this one to depth because the depth is the depth. And the direction is text. And we've got all these other things here. And it loads this information in. This core data is not for this well. It's just to show you how this is done, and we will have a look at the well that this comes from in another example. So if I look at the plot view, I have the plot view here, and I can choose a template. So the template I'm going to choose is the advanced log analysis. And I'm just going to use my finger to pinch and squeeze. And here we have the analysis of the well. So in order to do the analysis, LogScope is a cross-plot based analysis system. So if I tap on the cross plots, I have the cross plots displayed here. The first cross plot that you see when you open LogScope is blank and bland. And I'll just and you can plot anything by selecting the axes. With a touch screen, you can pinch and squeeze the points like so. You can use the region button and circle a bunch of points and perform many of these operations. You can create a flag, and the flag can be region or bad hole here, or you can put a regression line through that data, and it will give you a bunch of regression lines through that information. So if we tap on the template button, we have a bunch of predefined cross plots, and we have the ability to save the cross plot that we've created here, and we can save it as global, local, file, or you can actually email this to a colleague and they can use the same thing. So I'm going to save this as a local, and we call this like so. then we kind of get down to the interesting stuff, the log analysis. So if we click on the log analysis, we're looking at the first zone, and we have all the matrix lines plotted on the cross plot. And I'm just going to move to the reservoir zone, which is here. So we have the density plotted here on a scale of 1.9 to 2.9, and the neutron across the bottom, 0.1 to 0.6. And this is the standard as you would see it in a chart book. We have the three lines, which is sandstone, limestone, and dolomite. We then have a line defined by this point here, called N-phi matrix, rho matrix, and a point up here called N-phi 22, 2.2, which defines our matrix line. So I can move this like so, and I can move this point here. But I know that this reservoir is sandstone. If this was limestone, I'd move the point here. I know that the clays are here somewhere. Now, the reason I like the neutron density over all the other tools is they are quantitative tools. What they measure should be correct and should be accurate in terms of if it tells you that the density of the rock is 2.4, 2.3, or 2.2, it is 2.4, 2.3, or 2.2. Because that's what the tool is measuring. Whereas, if you have one gamma ray that measures a rock at 30 API, the next tool may measure it at 50 API, depending on how the calibration is with the tool. So that is what I call a qualitative measurement. So we want to get our quantitative measurement first, and the qualitative measurement second. On the cross plot, in addition to these points here that define the clay and the matrix line, we have a point that defines the phi matrix, phi max, which is the maximum porosity we're going to allow in the system. Obviously, we know the clastics can be packed to a maximum porosity of 48%, and nominally, because all rocks are going to have some amount of clay in them, we set this at 40%, or it's set nominally at 40%. We have a dry density of the clay point down here, and this is the clay with absolutely no water in it. And there is no clay without water in it. It's a very difficult point to actually measure, but typically this value is between 2.7 and 2.9 grams per cc, depending on what certain companies have certain rules about how that point should be set. Other companies will actually measure it or try and measure it. But finally, it's a point that shouldn't be moved unless you have very good reason to move it. On our cross plots, we have the histograms which show the minimum, maximum, and standard deviation of each of the axes, like so. At the top of the screen, we have the process button, And then we have options under setup, and we can show bad hole only or hide the bad hole, which can be set. You can reset the cross plot back to its default settings, but with your finger, if you've got a touch screen, you can actually pinch and squeeze the cross plot to however you want it. Now, this is okay looking at the cross plot on its own, but down the bottom of the screen you'll see that there's this sidebar icon that's been added as well. So if we tap on that, I'm tapping the wrong screen, we can actually see the parameters for that particular cross plot. Even better than that, by tapping on the log analysis button, you can actually change it so you've got a visual representation, and you can actually change these to suit. And here you can see the V clays. I can choose a V clay one, so we can see that properly. So we can see the V clay from the density neutron and the gamma ray here, and they're quite different. So as we work through the cross plot, here we have the sonic neutron cross plot. Again, this is exactly the same as you'd find. We know this is sandstone, so we need to move this point to there. We want this point over here because that's clay. So we've got the clay point and we've got the sandstone point. Not going to worry about phi max here. But here, because the DT clay is 129, we need to change the compaction factor. So that's down here, and we'll change that value to 1.3. So then we move to the next cross plot, which is the sonic versus the density versus the sonic cross plot. And you can see that this point is here. And then we have the M and N cross plot. And I'm just going to pinch and squeeze this up so that you can actually see. As you can see, this point here is down around the clay, and this M factor, N factor cross plot was developed for the Middle East for dealing with carbonates and so on. And then we have the gamma ray versus the sonic, and we can set our gamma ray points like so. And then we come to the gamma ray versus the resistivity cross plot. These points here, these are the points that are the hydrocarbon bearing points. So let's just pull up the composite plot, and we can see these points here. And I can switch on add region, and you will see that LogScope has the ability to allow you to highlight particular zones, and you can actually see those points showing up here, and you can know which is which are hydrocarbon bearing. I'm going to change this to a facies type and write this out as flag 1. And the reason I'm going to do that is that I'm going to make those be gas. So I'm changing this, and this point, this RW clean, RW gamma ray clean point, is the resistivity of is the salinity of the system, and this one here is the salinity in your clays. It's the bound resistivity of the bound water. So we'll just put that there, and then we move to the next, and the next few cross plots, as you can see, like here. But I'm getting to a cross plot, this cross plot, because I actually want this clay point to be correct there. Then we've got other cross plots for coal. If we've got a spectral gamma ray, we can work out the volume of clays. And here we have a cross plot that allows us to enter the hydrocarbon density. And I know that this hydrocarbon is somewhere around 0.2. And as soon as we enter 0.2, it changes that to gas. So I'm going to change this one to 0.2. And this is the facies zone. This is the one that we created from those points. And I'm going to go back. I'm going to make this 1.8. The original 1.8, because that's going to be below the gas zone. And then I'll just go back and produce this plot, and then we can hit the process button. And as you can see, it's changed all these to gas. You look at the gamma ray and the neutron density are matching really nicely, which means that we've got a good agreement between the two of them in terms of computing RV clay. If I go back to the plot, we can see here in this track here the gamma ray and the neutron density. And here we have the saturation calculated and the and the permeability. These bars here represent the net reservoir and the pay interval. And if we go to the report, we can produce statistics for a particular interval, or we can produce a hydrocarbon volume report by zone. And this is in meters, but we'll do this in feet. And there you can see it gives you all the information, and you can export that as a CSV file. So that's the hydrocarbon volume report. So we're going to talk about TOC, the TOC computation. So if we move to the cross plots, and we go to the resistivity versus versus density, we can move this point that we call the RT blind, and this is based on Passey's method of calculating TOC. So basically, for each of the tools, you have to define the point where you think the resistivity and the neutron, or in this previous case, the resistivity and the density, both measuring 0% TOC. And we're looking at the gamma ray values that are over 120. So that means these over here. So if we go to the sonic, we can do the same thing here. And when we hit process, it will compute that. And if we go back to the plots, we can actually look at the TOC. And there we have the TOC and the kerogen and the shale gas calculated over that particular interval. Okay. We will repeat the same process on the iPhone and the iPad. So I'm just going to select these wells as none, so they're not selected. And then we'll zoom to all the wells, and then we're going to grab the example well, which is here, and I'm going to go to 1:2000. Show zones, and we call this reservoir. And then OK. Then log analysis. So if we select all zones, we can type in SW equation. And again here, we have all the equations here. So we'll take the Indonesia equation. We'll just hit the run button. And we'll select none. And then we'll go to the cross plots. And we'll go to the neutron density. And we'll go here. I have the same functionality. I can bring the plot in by the side, or I can look at the parameters and everything. But I'll just quickly do this. This is on an iPhone, but it's got the full functionality of everything that I did before. And so I'm going to go through to the UMTA, row MTA plot and squeeze that up. I can do that there. And then we can go and deal with the and then I can just say process, and I go back, and then I load the template, which is the advanced log analysis, and then I scroll down. And once this is completed, so if we go to the example and load, and change the scale to 2000. And there we have the reservoir zone there. And you can see the neutron density and the gamma ray are reasonably good there. So we've had quite a few people are using this for deviated wells. And this well here, which I'll just show the full plot, is a deviated well. And you can show it like so. So if I go back to the so if I open Mari 1, which is the deviated well here, we have the same thing here. You can set the settings. You can have a different horizontal scale to vertical. And when you hold your finger down on it or the mouse button down on it, it gives you the value, measured depth, and so on. If we switch on the zones, you have the zones there, and you can add the zones in by yourself. Now we're coming to the last part of this webinar, and I just wanted to show you the multi-well capability. So we're going to use this Bliner wells again and the multi-well analysis. So we'll just choose Bliner, and we'll just choose the neutron density. I'll just get this set up so that you can actually see. So basically, LogScope allows you to evaluate multiple wells, and we've done a processing job with over 1,800 wells, and we have the ability to save this setup as a project. The processes that you can use are exactly the same as an individual well. The inputs are set up in exactly the same way. If let's say a curve exists, you can set it like so, and then you can use that to search all the other wells, and it will set them to that. And then the parameter store. So we have parameter mapping, and we have nearest, or we have a multi-well. And then you can process any or all of the zones. You can look at the zone parameters on a per well basis. You can do a hydrocarbon volume report of all the wells, and you can look at each well and look at the formation tops. You can set the log, and it will show you the log there, and you can apply some normalization. You can do it over all zones or just one zone, and then we'll switch to the output, and then when you run the analysis, we'll run it on all wells. It does that, and it updates the data like so. You can move the points on the cross plot as you would, and it populates this box down in the left-hand corner with those values, and you can scroll through the cross plots. We calculate the brittleness, and if I go into one of the wells, I'm going to load the rock mechanics template, and basically you have computed all the rock mechanics curves, including brittleness, fracture moduli, which is the inverse of fracture toughness, acoustic impedance, Poisson's ratio, a recomputed sonic, and a recomputed shear sonic. So you can create those curves, and you can actually produce the outputs. And in this case, this is done on all those wells. average values can be obtained for the information. In the next version of LogScope, we will be able to produce shape files which you can import directly into geographics and any other application that is able to import shape files. So when you do the multi-well analysis, you can actually produce heat maps of your parameters, of hydrocarbon bottom report parameters, and the input parameters used for the formation. This session, I guess this pretty much ends the webinar. The recorded session will be available, I think it's probably about 2 hours after the webinar finishes, and it will be automatically there, so you can access the session by simply using the same email and the same link that you used to join the webinar. So that's kind of pretty much it. We thank you for your time, and look forward to hearing from you.